Okie dokie. All right, so we're going to start transitioning towards wrapping up our stuff with graphs and moving towards compression, but we'll finish up by at least writing a single pass on Dijkstra's algorithm. So if you remember last class, we finished up kind of creating effectively what we have is two graphs, right? We have a graph that's based in a town collection where we have a bunch of towns and those towns happen to be linked to other towns. We also have a graph that's based in a road collection, which is a bunch of roads that happen to have interconnected towns. So these are two different bodies that would be considered legal graphs. But we would need something we discussed. I don't remember if it was last class or the class before that, but you know, the idea, like with a tree has a starting point, the root of the tree, where with a graph, you kind of have to pick a starting point. And that's sort of the point when we talk about uses of graphs. Now, there's lots of different uses for graphs, but most of them are kind of mathy type stuff. Maybe I'd say they're not overly practical for, let's say maybe us. So that's why this idea of the traveling salesman problem at the big level is most interesting to us with graphs, because effectively a graph is a way of generating what we envision a map looking like. Okay, so now the idea though is if we are looking at a map, graph map, we can use those interchangeably for the moment, but don't get too caught up in using them interchangeably, because a lot of programming languages have a built-in data type called a map, and that usually behaves kind of like a well, would behave as something like a hash. Sometimes they're called hash maps, but it implements something called a hash table. And a hash table is a whole different animal that we might talk about. Well, I mean, I could talk about it here just at the high level. The way a hash table works is if you have 10 values, you would apply some sort of hashing algorithm to each value. So what is a hashing algorithm? I'll insert it into the notes here. Because it is related to what we're talking about here is don't get confused with map built-in data structures or data types. Map is built into a programming language, is often an implementation of a hash table, often called a hash map. So to talk about hash tables, hash maps, any of those things, we have to know what is hashing. So a hashing algorithm is a function that when applied, well, before I even go any farther, anybody in here know what a hashing algorithm does? Before I get some audience participation. They're pretty heavily used actually in cybersecurity. In fact, you've probably seen one before on websites or something called MD5, Message Digest 5. So a hashing algorithm is a function that when applied to data, and I'm going to specify here, of arbitrary size, which means that it does not matter how big or small that data is, which is kind of the kicker here with hashing algorithms. So a hashing algorithm is a function that when applied to data of arbitrary size produces a fixed sized output. So an example of this might be, example is MD5, which can be applied to any size input and produces, what's the output size of MD5? Let's say it's 64-bit. See if I can confirm that for us here. Doesn't really matter what the answer is, the 128 bits. So the idea here is that if you were to feed it 1 gigabyte of data, it would produce 128-bit output. So a 128-bit number, you can think of it like that. If you fed it 2 kilobytes of data, it would produce 128-bit output. So how many unique 128-bit outputs are there? I say only. There are only 2 to the 128th power unique outputs for MD5. So that is 2 to the 128th, which is this value. 1, 2, 3, 4, 5, 6, 7, 8, 9. So that's 29 more. So that number always looks more impressive with commas. And I'm not even going to try to read it, but humongous number. But the important thing with hashing is it's not an infinite number. So if I'm allowing for arbitrary size inputs and producing a fixed size output, that means that my number of outputs here are only this many unique outputs. Yet I might have 10 times that in potential inputs. My potential inputs in this case are infinite. So that creates this concept of collisions, where you could have 2 values that are completely different than each other that just happen to hash to the same output, that happen to become the same 128-bit output. And those are called collisions. So what a hash map is a data structure that allows you to store stuff in an organized way. That is, you put stuff into, you could think of it like a linked list or something like that. You add to the hash map a value. It applies a hashing algorithm to it. We don't have to care what kind of hashing algorithm it is. We just know here that a hashing algorithm is an algorithm that takes an arbitrary size input and produces a fixed size output. So it gets its output and then it puts it at that bucket of the collection, so that when you go and you try to find, is something a member of a collection, is elephant stored inside of this hash map, you would apply the hash algorithm to elephant and then go and look at bucket, whatever that output number was, and say, is elephant here? Or is there something here? If there's something here, it's likely elephant. But since collisions do exist, it might not necessarily be elephant that's there. It might be something else that happened to hash to the same thing that elephant hashed to. All right, so this isn't something that's necessarily part of this class in terms of the details of hashing algorithms, but it is something that's pretty important in computer science, but it's pretty heavily used in cryptography and some network error checking stuff, like for instance, MD5. The reason I picked that, and I thought you maybe have seen it before, next time you're on some website that is like for downloading a large file. So if you go to like one of the Linux distribution websites and you download the latest version of SUSE Linux or something like that, one thing it'll have is it'll have an MD5 hash on the page somewhere where you can, so the idea is you just downloaded a 6 gigabyte file, let's say your ISO for installing Linux. Well, 6 gigabytes is a lot of bytes that might have some errors in it. Well, you can validate your accuracy of your download by running MD5 on your 6 gigabyte file, getting yourself 128-bit output, and you can compare that 128-bit output to the MD5 value they give you on the web page, which is, you know, just a pretty good size string, but not ridiculously long. So 128 bit would be 128 divided by, so that's 16 characters long. Is that right? 128 divided by 8 is 16 ASCII characters long. Or if you wanted to do Unicode, you can do something else, but usually ASCII characters are stored in 1 byte size. And that kind of validates, did I run into any network errors when I downloaded this file? If my MD5 hash of the file after I downloaded it matches the MD5 hash that they told me it should be, it's pretty likely that I didn't have any errors. Because in order for there to have been errors, 2 things would have had to happen. You would have had to have errors, and those errors had to be just the correct sequence of errors that your final data happened to still hash to the same correct value. And we're talking about some mathematical, highly improbable situations there. All right, but the punchline of all this for us is that if you look at many modern languages, they do have a map or hash map data type or object that you have available to you. And chances are that is not going to work like what we are describing our graph as being, even though we're applying our graph to solve the real world problem of representing a map. Okay, so tuck that hash table thing away in your brain somewhere. I'm not going to test you over that or anything, and I'll reiterate that when we start talking about the final exam here in a couple of weeks. But it is important CS info for you to have tucked away somewhere. All right, so now let's just talk about at the high level Dijkstra's algorithm. Now we're not going to go through and solve the entire traveling salesman problem. Instead, we're going to apply Dijkstra's algorithm one time as we go through here. So if we were to say what Dijkstra's algorithm does is it finds the shortest path between 2 points. Whereas the traveling salesman problem is we want to find the shortest path between a point and an endpoint, making sure that we pass through all other points in between. So you use Dijkstra's algorithm in abundance to, well, one way of solving the traveling salesman problem is to continually apply Dijkstra's algorithm from new starting locations to ultimately get yourself the best path to the end. And that'll make some sense after we kind of talk through this today. But Dijkstra's algorithm itself is only solving the problem of what is the shortest path between point A and point B, given potential other, in our example, what's the shortest path between town A and town B, given that we might have the ability to travel through some other towns to get there. All right, so that's what this guy is effectively solving for. All right, and this tells some information about what it is and things like that, but what I just said is pretty much the punchline of this guy. So what I have here is several different states that a map might be in. So we can imagine this guy being our map, where in this case we have 4 towns. Okay, so now initially, when we look at this, we're effectively marking up our towns with some pieces of information. All right, so this left one is the one we care about initially, and that's this, where right now they have the infinity symbol there. That's this distance. All right, so what you do first with Dijkstra's algorithm is you create a queue of all possible destinations. All right, so we have A, B, C, and D, A, B, C, and D. These are a queue of all of our towns from in our example. Okay, and when we apply Dijkstra's algorithm, when it's done, we will effectively have something that looks like this, with all of our towns having some additional information added to them, kind of marking them up. This will make sense here in a minute once we kind of go through this. Okay, so as we start processing our queue, so our starting point is this. We have a queue filled up with all the nodes we might want to visit. And we had to pre-select our starting location. So in this case, we're going to say our home base is A. And we have our queue. We're going to dequeue from our queue, grab the first element, which is an A. All right. And we're going to go ahead and let me move this here. A is our starting location. So since the thing we're currently looking at is A, we're going to go ahead and we're going to mark our starting location as 0. The distance from A to A is 0. Okay. Now, to get from, so we already replaced that infinity symbol there to 0. So our starting location will always have a distance of 0. The distance from your starting location to your starting location is 0. Makes reasonable sense. All right, so now if we look at this town A, we see there are 2 roads leading out of town. Now, Dijkstra's algorithm can work for a directed or an undirected graph. We've made our graphs undirected, right? We've said that roads link 2 towns and they go in both directions. So we didn't create a scenario where Port Washington heads north from Mequon to Grafton, but you can't take it south. So in our world, every one of these arrows would be 2 directional, right? A to B is 3, B to A is also 3. All right, so this works. The same algorithm works. You don't have to apply it differently. You would just assume there's a road coming back. All right, but from A's perspective, we have 2 places we can go. We can go from A to B. We can also go from A to C. All right, so what we do is our goal here is to add some information to our destination based on what it took to get here from our previous place. From our start, really, it's in this case, what we're actually adding is what did it take to get here from our selected starting point, where A is our selected starting point. All right, so to get from A, which has a base of 0, we didn't have to get anywhere to get there, to B, it has a distance of 3. So 0 to 0 plus 3 is 3. So we can say that's 3 miles. Is 3 miles better than infinity? Is that a better distance? Is it a closer distance than infinity? It would be, because infinity is going to make us pretty nervous. So notice here that we've replaced that distance here to a 3. The distance from A to B is no longer infinity. We can get to this destination B from our starting location by traveling 3 miles. We just want to use that in our example here. All right. Similarly, from our current starting location A, we can go take this road and get to C. And we would say that, okay, 0 plus 7 is 7. Is 7 less than infinity? It is. So we'll replace that infinity with 7. So this presumably would be like another field that this guy might hold. Okay, C would hold an additional piece of information. Okay, so after we've processed A, so for A, our starting town, well, A was our starting town that was pre-marked, and then it was also the first thing we pulled out of our queue of things that we need to meet. We marked up 2 things. We said that the distance to A from A is 0. The distance from A to B is 3. The distance from A to C is 7. All right, so we've added some additional information to the nodes of our graph. All right, so we've now hit all the roads coming out of A. So now we're going to finish using A here, and we're going to DQ our, so we're going to keep doing this as long as we have stuff in our queue, nodes in our queue. So we'll go ahead and DQ a B. All right, so from B's perspective, so B is our new perspective that we're visiting, viewing the world through. From B's perspective, and notice this is different than the way we've set ours up. With B, with this particular graph, this road, this distance of 3 doesn't go back. It's a one-directional thing. All right, so from B, we can only go to C or we can go to D. We can go from C or we can go to D. All right, so we can go ahead and we'll say, it doesn't matter which order we do these in. So we'll say, okay, well, I'm going to go ahead and go from B to C. So we're from a particular node, we would loop through all of the exits for all of the roads that come from that town in our world. So from this particular town, we can take 2 different roads. This road has a value of 5 associated with it. So that is our current value, which is a 3, plus a 5, which is an 8, will get us to C. Is 8 less than 7? It's not. So we have not found a more efficient way of getting to C than we had previously found. So I'm not going to update this C to be an 8 because a 7 was a better choice. All right, so we've done our work for that road. It's not like we abandoned it. We just said we're going to do the math. We're going to take this road. It's going to be our value 3 plus the power of the road, which is 8. And then we'll compare it to the current value at the destination. Is 8 less than 7? It's not, so don't change it. All right, then we'll take the next road. The next road is this guy with a 1. 3 plus 1 is 4. Is 4 less than infinity? It was still infinity. It is. 4 sounds a whole lot better than forever. So we'll go ahead and replace that infinity with a 4. So again, we're probably storing this as a field in our towns. Okay. So there's our 4. And then we can say we've dealt with all of the roads coming out of B. So from our starting point of B in this case, as we're going through our queue of all our towns, from B, we have dealt with the 2 roads that lead there in terms of the distance that B already was from A. All right, so that's why this guy was a 3, because it was a distance of 3 from our selected starting location. 3 got us here. So B started off as a 3. 3 plus 1 is a 4. That's what it took to get to a D. 3 plus 5 is an 8. That's what it took to get to a C, which isn't as good as our original path to a C, which was only 7. All right, so we've marked those couple things up. So we're done with the B. All right, now we can go ahead and do the math on the C. Notice I've skipped the picture for C here, but we can just deal with it real quick here. Let's assume that we DQ to C here. So we're done with B. We DQ a C. So now we're sitting here looking at the value of C. C only has one road leaving it, because again, this is a directed graph. So C has one road leading it, which was a 9. 9 plus 7 is a 16. Is 16 less than 4? Not even close. So we're not changing the 4. I have a neighbor that always takes back country roads to everything. He never wants to take interstates or stuff, and it takes him 4 times longer to get everywhere. But so if you want the scenic route, maybe you go A to C to D. But clearly, going from C to D by way of 9, 9 plus 7 is 16. 16 does not replace our 4. All right, so we actually didn't change anything on our graph when we were processing the C. And we only had to deal with one road for C because we only had one road leaving C. Now you have to keep in mind with our graph, since our graph is an undirected graph, that means all roads go 2 ways. We will need to remember where we haven't gone before. Now, let's just, we'll do that as a second pass. So let's just keep going with the directed thing here, and then we'll do it again, pretending like this is our graph. That is to say that we actually have, be a little hard in this particular case, since technically this is, in our case, we would only have one road connecting C and D, and it would be the same distance. Where here, there's like 2 roads, there's a distance of 9, and then there's like this super highway. that's a distance of 2. But we'll be able to fake it a little bit just to put it in context. But in any case, we'll just keep going with the current example where it is a directed graph. So from C's perspective, only one road leads out of here, even though there's a whole bunch of arrows involved. All right, so we don't update our graph at all relative to our current value of C. So we move on to our next value of D. So from D's perspective, there's only one road leading out of D. All right, which is a 2. D's current value is a 4. That's its distance from our selected starting location. 3 plus 1 is 4. That's why D is 4. So 4 plus 2 is a 6. Is 6 less than 7? It is. So we will replace the 7 that used to be associated with C as our destination with a 6. Okay, so when all is said and done, after we've processed through this queue of all our starting locations, we're left with a graph with finalized numbers. So this is our graph with this extra field that we kept track of. And notice that we updated actually a couple of things. Now, I was only talking about updating the numbers, but also notice that we updated the value, how to get there. So before A to C, C had a value of 7, and that was by way of A. When we updated it to a 6, 3 plus 1 plus 2, which is a 6, that was by way of D. So we actually updated 2 separate fields here. Not only the better number, but also where we came from to achieve that better value. We just came from D rather than whatever it originally was. Okay, so back to our very beginning example here. A to C was a distance of 7. 7 was better than infinity. So now we have a 7 here by way of A. We have a 3 here by way of A. We have a 4 here by way of B. We have a 6 here by way of D, so on and so forth. So in the end, we've marked up our graph in this way. Okay. So we need to, kind of thinking about this from the homework perspective, every one of our towns needs to have 2 more fields added to it. One is going to be the distance, and the other one is going to be the town that we would come from to get to this best value. All right. So in the end, our graph looks like this. And because we're implementing Dijkstra's algorithm, which only solves the problem of how do we get from a starting location, a pre-selected starting location. So in this case, we've just decided that our starting location is A. So when you're testing Dijkstra's algorithm, it doesn't matter which town you pick as your starting location, you will get a different graph potentially, or a different marked up graph potentially, depending on what your starting location is. But if I pick Mequon, my other towns might have different values associated with them if that was my starting location, as opposed to if I pick Saukville, for example. Okay, so in the end, after we've applied Dijkstra's algorithm, I now have a graph with some extra information. Every single one of my towns has two values associated with it. The distance it took to get here, total, from my selected starting location, and the town I went to right before I got here. Okay, so if I say I want to get to destination C, so if I say what's the best way to get from A to C, I already know that my starting location was A. And now I'm going to say, well, what's the fastest path to get to C? Well, I can just look at town C and see, oh, the fastest path to get here was a total of 6 miles. Then I might ask the question, okay, well, what was that path? How did you get to C using 6 miles? And that's where you have to walk your graph until you get to your starting location. So from C's perspective, it tells me the place I need to go from here is D. So I'm going to go from C to D. From D's perspective, the place I need to go that I'll say, is D my starting location? It's not. D is not A. So where do I need to go from D? I need to go to B. Is this my starting location? It's not. B is not A. So where do I need to go from here? I need to go to A. So here's this. Is this my starting location? It is. A is equal to A. So the path, the shortest path between A and C is the path that is A to B to D to C. That is the shortest traveled path between A and C in this case, a directed graph, because these roads only went one direction. All right, questions about how we came up with these numbers? Should be pretty straightforward, but just a little tedious. Okay, so now let's go back here and just make another pass on this, but we'll make the assumption that that we're dealing with our graph. And our graph is undirected. All right. And actually, why don't we actually just use our graph? That'll probably make the most sense. Okay. So we're going to keep a couple of other pieces of information about each of these guys. Let's see, how do I want to represent that? I think I'm just going to do text boxes. And this will allow you to check your work for the homework too, assuming you pick the same start town as we pick. All right. And the first question mark here is like our infinity symbol from the other thing. All right, so we need to pick a a starting location here. So we can pick, you want to just, we'll go wherever Concordia is. So we'll pick Mequon as our starting location. Okay. So now we start off here and we need our Q. And I'm going to get my Q this way. Oh man, perfect fit. All right, so this is my queue of locations. So we'll go ahead and we'll DQ our first thing, Mequon. So the distance from Mequon to itself, from my starting location, Mequon, to itself will be 0. Null value there or something like that. Okay. All right, so that's what it took to get to there. So we're done with Mequon. Throw that guy out. Next guy, Cedarburg. All right, so from Cedarburg, well, actually, hold on. I'm not quite done with Mequon yet. Sorry. So Mequon to himself is 0, and we don't need to go by way of anything. But now we need to look at the 2 roads that come out of Mequon. One going to Cedarburg and one going to Grafton. So Cedarburg is going to be an 8 plus a 0. So 8 plus 0 is 8. Is 8 better than infinity? It is. So we'll change this guy to be an 8 by way of Mequon. Similarly, Grafton is a 0 plus a 10, which is 10. Is 10 better than infinity? It is. So this is 10 by way of Mequon. Okay. Now we're done with this guy. So we'll go to our next starting place, Cedarburg. All right, so Cedarburg, there are 2 roads coming out of Cedarburg. One goes back to Mequon. We know we've already traveled that road, but we see it solves itself. So 8 plus 8 is 16. Is 16 less than 0? It's not. So we're not going to update anything here. Then we also have Cedarburg to Grafton. 8 plus 4 is 12. Is 12 less than 10? It is not. So we won't update anything. All right, that makes sense. Why we did what we just did and why we did not update anything. We took the starting value of Cedarburg, which is 8. We looked at the 2 roads coming out of Cedarburg. One was this one. 8 plus 8 is 16. 16 was not less than 0, so we made no change here. We took 8 plus 4 is 12. 12 is not less than 10, so we made no change here. Now we're done with Cedarburg. Go on to Grafton. From Grafton's perspective, we have 4 roads. So we have Grafton leading back to Mequon. So this is a 10. So 10 plus 10 is 20. Is 20 less than 0? No, so no change. We have 10 plus 4 is 14. Is 14 less than 8? No, so no change. We have 10 plus 7, which is 17. Is 17 less than infinity? It is. So this will be a 17 by way of Grafton. And then we also have a 10 plus 8, which is 18. Is 18 better than infinity? It is. So this is 18 by way of Grafton. All right. So we've handled the roads coming out of Grafton now. So we're done with Grafton. Go to Saukville. From Saukville's perspective, we have 3 roads. So this one is 18 plus 8, which is 26. Is 26 less than 10? It's not. So we make no change there. We have 18 plus 3, which is 21. Is 21 less than 17? It's not. So no change there. We have 18 plus 5, which is 23. Is 23 less than infinity? It is. So this becomes a 23 by way of Saukville. Now we finished processing all of Saukville. Now we go to Port Washington. Port Washington has 3 roads. So we have 17 plus 7, which is 24. Is 24 less than 10? Nope, so no change there. We have 17 plus 3, which is 20. Is 20 less than 18? Nope. So we no change there. We have 17 plus 8, which is 25. Is 25 less than infinity? Yes, it is. So this is 25 by way of Port Washington. Shrink that down just a skosh. All right. So now we've handled all the roads coming out of Port Washington. Now we're looking at Fredonia. Fredonia has 2 roads coming out of it. One is a 5, so 23 plus 5 is 28. Is 28 less than 18? It's not, so we make no change there. We have 23 plus 6, which is 29. Is 29 less than 25? No, it's not, so we make no change there. And we're done with Fredonia. Then we look at Belgium. Belgium has 2 roads coming out of it. 25 plus 6 is a 31. Is 31 less than 23? It's not, so we make no change there. 25 plus 8 is 33. Is 33 less than 17? It's not, so we make no change there. So in the end, what we've done now is we've created a Dijkstra's algorithm mapping of our graph with the assumption that our start location is Mequon. So that means what's the shortest path to get to Belgium from Mequon? Well, the total distance will be 25 miles. And how did you get there? Well, I went from Belgium to Port Washington, then from Port Washington to Grafton, and then from Grafton to Mequon. That was the best path to get to Belgium. What about from Fredonia? From Fredonia, it was a 23 total miles from Mequon. How did I get there? I went from Fredonia to Saukville. I went from Saukville to Grafton, and then I went from Grafton to Mequon. From Cedarburg, it was 8 miles. How did I get there? I went from Cedarburg to Mequon. From Port Washington, it was 17 miles. I went from Port Washington to Grafton, Grafton to Mequon. All right, so questions how this works. So applying Dijkstra's algorithm a single time allows me to mark up my graph with information that gives me the distance to all other locations, the shortest distance to all other locations from a selected starting location. Now, if you were to extend that into what you would do if you were to try to solve the traveling salesman problem, is you would now need to have at each of these. So right now I'm storing one tuple of information or two new fields, right? So we can think of this as just a distance and the place I came from to get that distance. I would need this pair for every single city that can possibly get here in order to have each one of these nodes be able to operate off of all possible destinations. Because this information right here tells me what's the distance, what's the smallest distance to get to my known starting location, which is Mech 1. Well, that's 8. Smallest distance to get to my known starting location, Mech 1, which is 18. Smallest distance to get to my known starting location, which is Mech 1, 23. But I know that I can also get from Fredonia to, what if my starting location was Belgium? The distance would have only been 6, but that was a different starting location. So if I picked a different starting location than Mech 1, this guy would be marked up very different. To solve the traveling salesman problem, you really have to have all starting locations. So you have to apply Dijkstra's algorithm for every single possible starting location, for every possible destination, so that you have all the information you might need available to you to build the map for visiting every single town in the right order from all the different locations. All right, so homework. Update our code, and I'll give you a starting point for our code. Make sure it's, there it is. Make sure it's saved. It is. Just make sure it runs real quick. I didn't change it at all, so oh, there's no output, so it's not going to do anything right now. Save this, so that's updating our code. Pick a starting location. Maybe Mech 1 to match our example on the previous slide. Dijkstra. Dijk. There you go. Algorithm to the graph, keeping track of the shortest distance and the previous town needed to get there for all towns on our graph. Display this info for all towns to prove it worked. And since you have a town collection, you have a pretty convenient way of looping through all of your towns. All right, questions, and this is due on Friday. This shouldn't be too bad. This is going to be literally going back and doing what we just did by hand when we did this guy. And remember, last class, we taught every single one of our towns to know about all the roads that come out of that town. So now for each of your towns, you'll be able to follow all the roads. So this really should not be too bad. All right, questions, what I'm asking you to do? All right, I will see everybody on Friday.